Welcome back, everybody. So we've just finished a practical part with PostgreSQL. So what it means concretely is that you can use the course Docker with PostgreSQL pre-installed and the data sets in there, and you can just play with it, right? You can just create tables, rename tables. You will have exercises as well, and test everything, especially this primary key, foreign key, play with it. It's the best way to understand how it works. Do not worry about making things wrong if you delete too much or, completely mess with the data sets. You can just reset everything in the worst case. Yes? Can SQL mess up a computer? I try to understand. We'll try to understand what he means, or she. No. I'm sure that they meant something. That they had something in mind when they told me. So I just check and we'll see. But I don't think that SQL is really dangerous. I think that it might be if you already have a SQL database running on your machine with extra data, then you have to be careful, right? But I assume that most of you don't have anything. Right, so I think you're normally safe with using the Docker and SQL, right? Okay. No. There's nothing to be scared about. SQL is even much easier to learn than many programming languages. All right. So let's now continue with the theoretical part. This one will not crash your machines, guaranteed. So we have yet another theoretical part, and I'm starting with a recap of what we had before, which is that we have a formal definition, a mathematical definition of what a relational table is. And technically, a relational table is a set of maps. We call these maps records, but it's a set of maps that additionally fulfills relational integrity, domain integrity, atomic integrity. It's these three additional constraints. If we have these three constraints, then we have a relational table, right? And without these constraints, that's big data for engineers. That's what we do next semester. But in this course, we have these three constraints, right? Then we can draw these beautiful tables with rows and columns. So we know how to define them, and now we want to learn how to manipulate them. And who says manipulate? With math means we need to define all kinds of mathematical tools in order to manipulate these tables. So what we are going to deal with now is no longer data definition. Data definition is what we've covered in the previous lecture, right? With create table, drop table, rename column, and so on. Technically, the insert into part was already DML because you were actually manipulating data. But now this is DML taken to the next level of data manipulation. So the name for that is relational algebra. So you see, it's already sounding very fancy. So it's the relational algebra that just takes tables and creates tables and transforms tables and so on. So it's like an enormous calculator, except that in the calculator, you don't have numbers, you have tables. That's pretty much what we are about to do. So you know already, I assume from primary school, that you can take numbers and combine them through addition, multiplication, subtraction, division. It might sound trivial, but actually there was a revolution that only happened 2 centuries ago via a mathematician known as Évariste Galois, who had the idea of abstracting away from numbers the notion of addition, multiplication, and so on, by generalizing to anything. The idea of having an operation that you might call plus, and then you have some sets with objects in there. Then you take an object and combine it with another object via some operation, plus, and you get another object. And then he suggested to abstract away a few properties of this plus. For example, the fact that you can just commute the two objects without changing the results, and that makes it commutative. You might have one of the object that when you plus it with something else, just delivers that something else. That's a neutral element. That would be 0 for addition. That would be 1 for multiplication. You might have elements that have an inverse, right? If you add an element with its inverse, so that's the general term, right? It would be the opposite for addition, but 2 plus minus 2 gives you 0, right? So there's this notion as well. And when he did that, actually, nobody took him seriously. Because it's like, what you're doing is just a toy. Like, who would even need that? We already know how addition and multiplication works. So why do we even need that? But it turns out that Évariste Galois had just invented and seeded pretty much everything we do today. Group theory, groups, rings, fields, linear algebra, everything basically came from this finding. And in essence, what we are doing today is pretty much this, but except that the objects we're going to manipulate are going to be tables, right? So unfortunately, Évariste Galois died young. I think was only 19 when he died, and actually that's pretty impressive what he did in such a short amount of time. I can only imagine how the world would look today if he had lived until say 70 or 80. All the things he would have invented and that we would have today. But anyway, that's already a lot. So yeah. We are just, so that's another example, by the way, with matrices that you can also, who saw matrices already? That's linear algebra, right? You can, it's basically these sort of cupboards in which you put numbers and you can just manipulate them in this way, also add, multiply, and so on. I have a lot of respect for them because there is a theory in mathematics called representation theory that says that these cupboards of numbers, they are actually generic enough to be able to pretty much represent any group. And that's actually quite a strong statement. So extremely powerful. However, what we'll do is the same with tables. So we'll take tables and we'll do all sorts of things with these tables. And I'm going to teach you all of the operations that we can apply to these tables. Can be two tables combined to one. You can also have a unique table that you turn into another table. So that's called the unary operator. And when you have two, it's called the binary operator. You can even imagine more than that. All right. So in the beautiful world of the relational algebra, we have several categories of things that we can do. We have the set queries. We can compute the union, the intersection of the subtraction of tables. We can filter tables with projection or selection. We can rename tables, creating a new one. So relation renaming, relational table renaming, attribute renaming. We can have this, what is called shuffling queries. So it will become clear why it's called shuffling in big data for engineers, but I just call them this way. It's when you group and when you sort. And then you have the joining queries. These are the expensive ones that create a Cartesian product, natural join, theta join, and so on, right? Welcome to the beautiful world of the relational algebra, and this is the math of relational tables. All right, so that's a relational table. It looks like this. I'm going to take simple examples with plenty of fake numbers and letters. Well, actually, these are real numbers and letters, but it's just that they don't mean anything. The first thing I'm going to do, but it shouldn't surprise you because we've already done that when we had our practical course, is that I'm adding a name to the relational tables there in this row. So I'm calling it R. They have a fancy name for that. I think in the book, I barely use that, but apparently they call it a relvar for relational variable. So it's like a relational table that knows its name. Now, as a mathematician, it itches me a bit because normally when you assign values to mathematical variables, the values are not supposed to know the name of the variable that they're assigned to, right? If you say x equals 2 and you ask 2, what is your name? They are not going to answer x, right? They don't know, it's just 2, right? And here it's kind of in between because now you have this relational table, you call it R, and then you ask the relational table, what is your name? It's going to say R because it knows. So this is why it's a bit different from the typical mathematical variables. It's really a relational table that knows its name. It carries it with itself, okay? So I'm just going to have this name all the way, but this is pretty much what you have in PostgreSQL, right? All of the relational tables, they have a name and you can change that name. All right, I'm just saying that so that you don't confuse it with actual mathematical variables because this is really a bit different. All right, but it's a minor detail anyway. So now I'm going to go through the whole menu of what you can do with tables. I take them one by one, and we'll just take the time today and next week to go through them. And I will have plenty of animations, of queries, formal definitions, but I'm going to try to not scare you too much with the formal definitions. All right, so let's go ahead. Set queries. Why set queries? Well, you remember I told you a relational table is a set of maps, right? So obviously everything we can do with sets, we can do with relational tables because they are sets. I need a few definitions just before. The notion of a closure of a set under a certain operation. So I have a set that I call A. It has 4 elements. And I have some operation, unary, so it only takes 1 element. And when you apply this to an element, it gives you another element. In that example, I'm taking X, right? The orange circle. And I'm, circle. I'm just going to call it a circle. Doesn't matter. And I map it to this tilde X. So tilde is my operation. But what matters is that this tilde X is still in A. Right? It's not outside. It could be that you send it somewhere outside, right? But if it doesn't get outside, if it always stays inside, then you say that A has closure under this operation, right? It means that you never leave the set A, right? And this is important. Why? Because if we have relational tables and we combine them with an operation, we still want to get something that is also a relational table, right? Because if I combine them and I get something that is not a relational table, then I have a problem, right? That's no longer a relational algebra. All right. The same applies for binary operations like plus. For example, if you have X and Y and you combine them as X plus Y, then A has closure under plus if X plus Y is always in A when X and Y are in A, right? Does it make sense? Everybody with me? All right. Now, why am I saying that? Because it's actually important for the tables. So here are 2 tables, R and S. R has 2 columns, A and B. S has 3 columns, C, D, and E. They are tables, so they have domain integrity. So they have domains here. A is a string, B is an integer, C is an integer, D is a string, and E is a date. Now we want to combine these tables with set operations. For example, the union. Let's compute the union of these 2 relational tables and see what we are going to get. We can do it. Why? Because these are 2 sets of maps. So if I have 2 sets, I can pick the unions of 2 sets, right? I'm going to get a bigger set of maps, right? So this is a set of maps on the left. This is a set of maps on the right. So I can put them together. So just to make it explicit that these are sets of maps, I'm even putting the maps in there. So the value of A and B, C, D, and E for each one of them, right? You agree that these are sets of maps, right? This is the same. This is really the same thing. So now what is the union of these 2 sets? Well, I have 6 elements in one and 4 in the other. So I'm going to get how many elements? 10 in the union, right? So the union of these 2 is this set of maps that has 10 maps, right? Is that a relational table? I see a lot of no's, and indeed, that's not a relational table. Why? Exactly, the relational integrity is broken because they don't have all the same attributes, right? The first 6 have A and B, and the next 4 has C, D, E. So it's a collection of maps, it's a collection of records, but it's not a relational table, right? So it means that the set of relational table does not have closure under union, because we created something that's outside of the realm of relational tables. So the supers are not the same. All right. So it means concretely that if I want to compute the union or intersection or subtraction of 2 relational tables, I need to restrict a few things. I need to require that my 2 relational tables have the same attributes, the same column names. All right. So I did it. Okay. These are 2 relational tables that have the same set of columns, right? Right. But I have a second constraint, because you probably notice here that if I take the union of these 2, I will break which other integrity constraints? Column A is a string on the left, an integer on the right. So the union of the 2 will break, yes? Domain integrity. So we will break domain integrity. How do we avoid that? We must also require that the domains must be the same, right? So it has to be the same. And there is a third constraint that normally shouldn't be in there because the order doesn't matter, but in practice, PostgreSQL seems to kind of still have some internal order of columns. So this is just a small warning for the in practice part. But mathematically, it shouldn't matter because there is no order in a map anyway. So I'm just putting that as a warning for when we actually start using PostgreSQL after that. All right, so now that I've done this paperwork, we can check. Do we have the same attributes? Yes. Do we have the same domains? Yes. All right, I even put them in the same order in the way that they are drawn, just to not confuse you. So now, let's compute the union of these. It's a relational table that I'm going to call R union S, right? I'm starting using these fancy mathematical symbols that I call it T. So we have T. What are the columns of T? ABC. What are the domains of T? String, integer, Boolean. How many records or maps do I have? 7, exactly. I just take the union of what's called the extension. So I take the union of these two sets. That's it. I have just defined the union of two relational tables R and S, and it is also a relational table. Yes?
I'm searching for bar.
So here, there are absolutely no constraints in the sense that I can put whatever I want in the maps, right? If you start then defining constraints like unique, you want a name to be unique and so on, or you want something to exist, then this comes on top of that, right? But everything that I'm presenting here doesn't use any of the other constraints, right?
Let's say I say A is
yes, yeah, all right. So it might indeed be that you define A as the primary key, maybe because the primary key in R was A and in S it was A, right? So technically the table that you're creating here, it's a completely new table, right? So there is no reason why if A is a primary key for one of the two or the two on the left, there is no reason why it should be a primary key on the right as well. There is no reason for that. So here on the right, nothing is a primary key, nothing is unique, nothing is not null, right? You could, however, store it as a new table and then alter it to make it a primary key, but it might require that you do a bit of cleanup before you do that, right? In fact, a lot of people spend a lot of time cleaning up data, doing that sort of things, right? But for our purpose, there are no constraints at all. There is no primary key, nothing. So this is absolutely not a problem that bar appears multiple times because I didn't put any constraint for that. Just sets of maps, right? Okay, we had another question. I think another, you also? No other questions? Okay, so I think I saw raised hands. And on Zoom, no question. All right, let me continue then. Here, oh, I think I meant to create a duplicate, but I forget to update this here. So here, there are no duplicates, right? Because these are sets of maps. Imagine that now I have twice the same records here. So it's not foo 3 true the second time, but foo 3 false. It could be that I have a map that is both in R and in S, right? So if that happens, then something else will have to be done, but technically it's done automatically by the math. It's just that whoever implements that in C++ have to deal with that. If they have twice, so here, everything is correct. So here I have foo 3 false on the left, foo 3 true on the right, so I have both of them. Here I changed the data, and now I changed in table S, I set C to false on that record. So now you probably notice that since we have the same map in R and S, since it's a set of maps, I can only have it once on the right, right? So it means that in general, if I have maps that appear in both tables, then I might have less than the sum of the numbers, right? I have 4 and 3, the sum would be 7, but I only have 6 maps on the right. Why? Because some of them were the same, and I have to make sure there are no duplicates, all right? Again, the math does it automatically because this is what sets are in mathematics, but if you implement it in C++, then of course the engineers of PostgreSQL need to actually do it by coding. For whom is that clear? right? If I take the union of two sets and then there is an element that appears in both sets, then obviously in the union it's appearing just once, right? It's just the definition of the union. Yes? There is no identity. So mathematically, foo3 false is just a value like the number 2, right? So if you have a set of integers and there is 2 in one set and 2 in the other set, in the union there's going to be 2, but there is nothing that allows you to say if 2 comes from the left or from the right, right? Because that's the value 2. It's set, so the position is totally arbitrary. I had to put them on my slide in a certain order, but since we are talking about sets, there is no particular order whatsoever. The position is totally irrelevant. I'll come back to the bags and lists, but now I'm just talking about sets, right? Okay. All right. Let's continue with intersection. So if I do the intersection of these two, the intersection, I get a table that I call T. Same attributes, same domains. But now I'm only going to put the maps that appear on both sides, both in R and both in S. Can you spot them? There's just these two normally. Foo1 true and foo3 false. You will find them on both sides. So these are the only survivors of the intersection, right? For whom is that clear? All right, I just computed the intersection of two tables, but again, with the requirement that the domains are the same and the columns are the same for relational integrity and domain integrity. Okay. Here, whoever implements that in C++ will not have to worry about duplicate elimination because when you compute the intersection, it's kind of just happening when you do it. So you don't have to worry too much about that. All right, and now the subtraction. What is a subtraction of two sets? If I do T minus S, well, it's technically everything that's in R, sorry, R minus S. It's everything that is in R, but that is not in S. So let's look at the 4 maps that are in R. I marked them actually. So this first map here is in S, throw away. This one here is not, I keep it. This here is in S here, so I throw it away. This one is not in S, I keep it. So the result is a relational table that's called T, same attributes, same domains, and I have these two tuples because they are not in S. These are the only ones that remain. This is R minus S, right? So we can do union, intersection, and subtraction of two sets. These are first three things that we can do with relational tables. All right, and you see I can even write these fancy mathematical formulas with the union, intersection, and minus, right? Mathematicians sometimes put the minus in an oblique fashion, like a backslash. You might have seen that too. All right, and here the engineers doing it in C++ also don't need to worry too much about the duplicates. Careful, careful, careful. Union and intersection commutes, but subtraction doesn't commute. So that means that R minus S is not the same thing as S minus R, but you probably already know it with numbers too, right? So R minus S is the top table right there. S minus R is the table at the bottom, right? So just to make that clear, that the order of the two tables is then important. All right, so far so good. Yes, we have a question. Oh, in real life, I don't know, you have, imagine you are the Publica, so the pension fund of the employees of the Confederation or any other pension funds, and you have the relational table of all the insured persons who are contributing to the scheme. And then you have people who retire. So there is, let's say, another table with retired people. And then at some point, you want to make the subtraction of all the people that were insured minus those who are retired, and then you get the one who are working, right? That's just one example, but it's pretty much, you will find plenty of use cases like this in the real world, because in the end, this is the real world that we are dealing with. So all of these are basically building blocks that you can use in order to assemble queries. In the end, you'll see at the exam, the queries can be formulated in English, right? But then you have to map the English formulation of the query to something like this, and eventually to the SQL language. Right? Okay. So raise your hand if you're following. Okay, very good. On Zoom too, right? I assume that nobody fell asleep on Zoom. You're still with us on Zoom? Raise your hands. Yes, very good. Okay. So now let's move on to others. So we have filtering queries, selection projection. They only involve a relation. I have good news. If you've been using spreadsheet software, I'm pretty sure you've already done it there. So there are no constraints. That also makes our life easy. So we take any table. We have a question, I think.
The question is, I don't know whether this was explained, but how is it decided which of the duplicates is staying and which is eliminated?
Yes. So it's what I was trying to explain earlier, that the question of which one is kept is tied to the notion of identity of a tuple. Does a tuple have an identity? You really have to think of tuples as mathematical objects. So when you have a map here that says foo1 true, let's take in the intersection, foo1 true, the foo1 true in the R table is mathematically exactly the same as the foo1 true in the S table. These are just mathematical values, mathematical constructs, right? So there is no notion of an identity. It's not like there is one foo1 true that we can call Alice and the other one that we can call Bob. No. Mathematically, they are exactly the same thing. It's like 2 and 2. 2 is just 2. It's a number, right? So there is no notion of identity. But it's a very good question because in some languages, and I'm thinking also in NoSQL and big data for engineers, it sometimes happens that you do want to consider the identity of the values you're manipulating, and then you actually do care about whether it comes from the left and from the right. I can even give you an example. Imagine that you update something somewhere, then you will care about which one you updated, right? But here, it's just math. I'm not changing anything. I'm just manipulating mathematical objects, right? So this is why it doesn't matter. Did I answer your question? Yes? All right. We have another question here. The microphone, it's there. Easier because then everybody on Zoom also hears.
Yeah, no, I mean, because in SQL, the memory management is a bit more hidden, right? But like if you do it in C, we would actually care which one we take because it's stored at a different place, right?
Yep.
Here, we don't even know how it's stored.
That's pretty much the idea. Yes. Yeah. So indeed, so this has to do a lot with this notion of data independence. Technically, in C or C++ or Java, you would care. You would care about this because you might modify some of the objects. It's called the side effect. And then you do care which one you modified because you will see the changes. What is very important is that if we apply the data independence and we realize that this is just a mathematical model, this is not a programming language here. This is really math. We have mathematical objects that we manipulate. So we don't see any of that. We don't see any of the physical effects of what we are doing here. You might only see it when you start implementing it. But normally, if you have a good engine, if it's well implemented, then you shouldn't see any difference in terms of identity, right? But the question is a good question because indeed, it's tough to actually implement something that is truly data independent. It's not something that is so easy. And it's true that when you learn programming in C++, in Java, in Python, then the identity actually does matter. It might matter, right? Okay. All right. But I reiterate, this is math. It's just math that we are doing here. There is no computer in there. These are sets of maps. You don't need any computer for that. These are really just mathematical objects here. Okay. So, all right. Now, let me take this table. It has 4 maps, 4 records. The first thing that I can do is that I can take some attributes and throw away the others. That's called the projection. So an example is that I can keep A and C and throw away B, right? So I get a table that I call S. The attributes are A and C because that's what I wanted. I wanted to project to A and C. And that string and Boolean, it's the same domains. And now I have the values that were in there. What happens? I took away from every record, for every map, I took away the association with B. I just threw it away. You can do that with Excel, right? Just select a column and click delete or hide. That's pretty much something that you can do very visually, right? But we do have a very fancy mathematical notation with the letter pi for p projection. So we use pi. Pi has parameters. It's the name of the attributes you want to keep. So it's pi subscript AC. That tells we want to keep A and C. And that's a function applied to R, right? And so if we apply the projection to A and C, we apply it to the relation table R, we get S. Who agrees? Okay, I just say I'm projecting two attributes A and C and remove B. All right, that's what happens. Just be careful. You might be, if you're not careful when you compute that on paper, in that case, you have to notice that even though there was no duplicate, foo1 true and foo3 true, that's not a duplicate. But if you're not careful and you just copy things over, you might incorrectly put a duplicate in there, right? So it might be that when you project, you have less records because when you remove attributes, you're going to create duplicates. So you cannot just blindly copy over. You really have also to care when you compute it on paper of removing the duplicates. Right? Okay, let's look at the twin sister of projection, which is selection. It's the same thing, but on the rows. So if I want to select some of the rows, all I need is a predicate. It's a requirement on the rows that I want to keep. For example, my predicate could be B has to be smaller than or equal to 2. Everything that's smaller than or equal to 2, I keep, and everything else I throw away. So now what am I going to keep here? The first two rows, right? And I'm going to throw away the other two. Technically, my predicate can not just be smaller than or equal, right? It can also use smaller than, greater than, equal, different. I can even use arithmetics if I want. I can use logical operations like A plus B must be greater than C, and D minus C times E must be smaller than F, for example. That's a predicate, right? So this is kind of all the Lego building blocks that you can use for your predicates. So here I'm just using a simple one, but you can use all of these blocks that you can combine in some formula. And now I have my selection based on B smaller than or equal to 2. And I get a relational table with a new name. I call it S. It has the same attributes because I'm just selecting the rows. Same domains, but now I have less rows. It's a subset of the rows. I only kept the first ones because they are the ones who fulfill my predicate. For whom is that clear? Right. Who already did that in Excel or any spreadsheet software? Some of you. You know how to do it, right? You select all of the data table. You click on what is it called, data filter data or data filter or something. Then it adds these little knobs on the buttons on your headers. Then you can click on a header and then you can check the values you want to keep and uncheck the others. It's automatically going to filter out the data you want. So this is something you can do in a spreadsheet. So just to make sure that this is really something that is very visual to understand. Okay, and here, when you do it on paper, you don't need to worry about duplicates because it's anyway just copying over and it's just taking away some of them, right? Okay, that's the visual if you do it in spreadsheet software. Now, there is also something fancier that is some sort of extended projection. So in a projection, we just keep some attributes and throw away others. But in fact, you can also create new attributes computed from others. Here's an example. I'm going to project on A and C and create a new column that I call D. How am I going to populate it? By putting B plus 1 in there. So what do I get? S, A, C, and D, because that's what I have in my subscripts of pi. String Boolean integer, because B plus 1, that's also going to be an integer. And now I see foo true, bar false, that's all taken from the left. But you see that D now is 2, 3, 4, 5 instead of 1, 2 plus 3, 4, right? Because I added 1. That's called an extended projection. We'll all be able to do that with SQL, as we will see next week and the week after that. For whom is that clear? All right, so projection, selection, extended projection. Technically, you can do that in a spreadsheet software too, right, with formulas. Just put a formula, then you grab the little bottom right corner, and then you drag it down, and it's automatically going to create your values, right? Just so you have the visual. Okay, still have a few minutes. Renaming, that should be relatively easy. I keep using Greek letters, right? You notice the selection was a sigma. So we have pi and sigma already. And now for renaming, it's called rho, right? It's a Greek letter as well. It's the R technically in English, corresponds to the R. So now what do I do here? I rename A to D, right? So I put rho subscript A, a rho D. So what happens is I have a new relation. I call it S. What columns? Well, the same ones, except that A now is changed to D, right? So it's DBC, and then the rest is the same, because all I did was rename my column, right? That should be easy, right? I just renamed the column, but this is, we are dealing with math, so we still need a mathematical formula for doing that. What about renaming a relation? Well, technically in math, you cannot change things. You can just construct objects, right? So here you can just say S equals R, and now we have this new table that's called S. It has the same content as in R. Now I'm going to be honest with you, this itches me, because technically, mathematically, you shouldn't see any difference. It's an equality, and here there's still the difference in the name. So again, it's kind of math, but this notion of rel var is a bit pushing the mathematics to some limits, right? But yeah, it teaches a little bit, but just consider that whenever you write S equals, you're actually giving it that name, S. All right? There's another notation that I think is a bit cleaner, and I like this better because now the renaming is explicit. We really consider that R contains its name somewhere, and now we change, we swap R for S, and now we have a table called S. This mathematically is a bit cleaner, right? So I kind of like this better, but you might see also this abuse like that, right? This is better. So row S just says now it's called S. All right. Who wants to stop here? Who wants to continue a little bit? Okay, let me continue a little bit. I'll try to use most of the time left. We might have to interrupt in the middle, that's all. All right. Here's yet something else you can do called the Cartesian products. We actually already saw Cartesian products earlier. It's when you have two sets and you build all of the possible pairs that you can find in these sets. We just saw it in a different context. So now I'm going to literally build T as the Cartesian product of R and S. So what's going to happen is I'm creating a table called T. The attributes are going to be all of the attributes from both sides, right? A, B, C, D, E. These are my attributes. And now my records in there are going to be all of the possible combinations. Any pair that I can create from the left and from the right. So I have two possibilities on the left, 3 on the right, which gives me how many possibilities? 6. Here they are. So these are my 6 possibilities, and this is the Cartesian product of my 2 tables. So you see it's a set of maps, 6 maps of 5 attributes, and every map was obtained by merging or unioning, if you consider that you can union maps, but basically putting together maps from the left and from the right. Okay, for whom is that clear? Who could compute that on any other input tables? All right. Now, be careful. A word of warning, especially for the exam. Here, it's only 2 and 3. 2 and 3 is 6. Now, imagine that you have a table with 1,000,000 rows for R and another table with 1,000,000 rows for S. And you build the Cartesian product on that. What is that? Well, I don't know, because the computer is going to crash. Because technically, it's 1,000,000 times 1,000,000. You're looking at 1 trillion records. That will not fit on your laptop. So be very, very careful. If you compute the Cartesian product on your computer and the tables are too big, that might crash. In fact, this is dangerous. Maybe this is what the TA meant, I don't know. But you have to be careful. And some of the systems, and especially in big data, they even by default prevent you from computing Cartesian products to prevent that. And you can actually, if you feel adventurous, deactivate that and force the Cartesian product because you know what you're doing and so on. But just for the exam, you have to understand the queries you write, right? So in many cases, you will have a way of just resetting, but have that in mind that you must be careful to understand what you're building. Okay. Now, just a word of warning. What happens if we have a collision of attributes here? Then technically you cannot just go ahead and do the Cartesian product. You cannot, right? Because you're going to have a problem. So what you need to do first is to rename one of these. So let's rename B to E, and then you can do the Cartesian product, right? So this is also mathematically, you need you have a few constraints on what you can do, right? Some systems, that's more a practical thing. Mathematically, it makes no sense because that's not clean mathematically, but you will find that in some database textbooks, sadly. That they will basically still give you the Cartesian product, but then they will put R.B and S.B on the right? So they will basically automatically rename them by disambiguating with the name of the table, right? So you could consider that you force your way through a Cartesian product in this way. This is kind of cleaner, right? You really define the name that you want in there, okay? But you will find that probably at some places. And I think that if you try to do it in PostgreSQL, PostgreSQL is also going to do something like that. It's also going to put some table names in front so that you know where that actually came from, right? It has nothing to do with identity here. It's really that there has to be one of the columns that has the name, but because it's taken from R and the other taken from S, okay? All right, so this is pretty much what it does, the Cartesian product. And I'm going to, no, I don't want to scare you with that. We'll do it next week, the join. It's less dangerous than the Cartesian product, we will see, because it's a bit smaller. And the join is exactly what corresponds to this foreign key, primary key thing. When you have a foreign key referencing a primary key, you want to join them. So this is what it's for. But this will keep for next week, right? So let me just check that you followed. Of course, every time I need to reset. Just before you go, where is my screen? Is right there. So let me know. Oh, it works now. It's all fixed. Just checking that you followed. So you'll have exercises, of course, to practice this. So really do it. Do the exercises and write as much SQL as you can to create your tables and experiment around. There is no better way than actually practicing to understand everything, right? Okay, that actually looks good. So I leave you in the hands of the TAs, right? So you will have these exercises putting into practice, usually with a small offset of 1 week. Thank you very much. Enjoy the exercises, enjoy your weekends, and then I'll see you next week at 10 a.m. here for the continuation of the relational algebra. Thank you very much.